Hello, my name's Logan Wood. I'm a third-year student here at Colorado State University. I am enrolled in ECE 311, 331, and 341. So yeah, I'll be doing the full 7-minute video for you guys. So yeah, for this KI, we're looking at power management systems, and specifically we're looking at the use and application of them in cell phones, because this is most relevant to everyone's lives. So yeah, for this KI we had a full wave rectifier and a smoothing capacitor. So we're going to look at the importance of that and how taking an AC signal can be transformed into an all positive DC signal and why that's useful in everyday life. So yeah, jumping right into it. First, let's look at how a diode works. So you can see from the pictures in front of you two different orientations of a voltage source and a P-type and N-type semiconductor together. And basically what's happening here is when a voltage source is pointed towards the positive side is pointed towards the N-type of a semiconductor, or the blue region in this case, our depletion region is going to go and shrink and also result in less electric field. And vice versa, when the voltage source is orientated towards the P type of the semiconductor, or the red part for our purposes, the depletion region is going to go ahead and increase, and we're going to have more electric field. So now that we know how a diode works, let's go ahead and see how a diode works inside of a circuit. So looking at the circuit below, basically what's happening here is we have a sinusoidal waveform going into a diode and a half wave coming out as our output. So basically what's happening here, and this is the overall functionality of a diode in a circuit, it allows for positive sources or positive voltage to be passed through at a certain threshold value when the back of the diode, the non-hatted side, is going to allow a positive side to go through, and then the hatted side is going to allow negative sources to go through, and this ends up giving us an output of a half-wave rectified signal. So this is the basic building block and principle we're going to use to build our full wave rectifier. So moving on, if we actually look at our full wave rectifier circuit in our beautiful picture drawn by Dr. Roy, you can see how in the top figure we have voltage going out of the positive terminal of our output source, going through D1, around our circuit, back through the positive end of D2, and back into our source, and vice versa for our negative signal below. So this is important, and this is the current flow in our circuit, which is going to result in this output that you see on the right, which is going to be a fully rectified output source. I chose this figure specifically because our pre-work specified that we're using ideal diodes, which is not going to have a threshold voltage. As soon as voltage equals 0, our diode's going to go ahead and short. So we don't have a threshold voltage. But if we were using a constant voltage model for our diodes, at the bottom of these peaks, or at the bottom of this source, we would have a little gap, and that would be our threshold voltage gap in the time where the source is actually going to be an open rather than just letting voltage flow through. So moving on, we now have this fully rectified output, and this is going to go into our RC circuit. A capacitor is going to charge and produce an output, which you see on the right side of this. Basically what's happened here is we've taken originally a sinusoidal source, rectified it to give us all positive values, and then put it through an RC circuit, which is now going to result in a essentially a DC positive source, which is a very, very powerful tool for electronics. For example, most outputs in homes, or actually all outputs, use AC sources, but most all electronics use are DC dependent. So such as a full wave rectifying circuit with a smoothing capacitor, that could be a simple solution just right there to solve that problem. So going back through and connecting all of our courses and the importance of everything here, 311, you can look at the linearity of the circuit and time invariance of the system. So for our rectifying circuit, it's going to be nonlinear because diodes are nonlinear, and therefore our entire system is going to be nonlinear because we always have a positive output even when we have negative input. And our system's also going to be time invariant because the operation doesn't change over time. It's always going to be the same. Moving in the 331, we can look at the different states of the diodes. This is important because we can model the different outputs based off various different inputs and give us an estimation of what we should see from the circuit, which is a very powerful tool. It also gives us theoretical results of the circuits as well, which is very important. And finally, 341. This is going to go ahead and explain all the voltage and electric field inside of our diodes and just our overall circuit, which is very important to know. Of course, if you're going to do any useful circuit analysis of this system. And yeah, that's all I got for you guys. So thanks for listening. I appreciate it.